We see AI do these incredible things every single day, right? From making art to crunching insane amounts of data. But how does it actually work? Well, today we're going to pull back the curtain on a really fundamental idea in machine learning, the manifold hypothesis. It's kind of the secret sauce that explains how AI finds order in all the chaos.
Okay, let's just start with a cool example. Have a look at this. On the left, a photo of a dog. In the middle, a pencil sketch. And on the right, an AI has perfectly blended the two, redrawing that dog in the style of the sketch. I mean, it really does feel like magic. But how on earth can a machine do something that creative?
To get the challenge here, you gotta think like a computer for a second. That photo of the dog, it isn't a dog to the machine. It's just a bunch of data, a grid with millions of colored pixels, and every single one has its own number. So how does the AI go from that giant sea of numbers to understanding dog, or couch, or even an artistic style? So here's where the idea gets a little wild. Try to imagine a space where every single dimension corresponds to just one pixel. That means a 1 megapixel image would be a single point in a million-dimensional space. Our dog photo is just one tiny coordinate in this absolutely massive, unimaginable universe of data. Now, what's really fascinating is that almost all of that space is just, well, it's junk. If you picked a point in that space completely at random, you wouldn't get a picture of a dog or a cat or really anything at all. You just get meaningless static, like an old TV with no signal. The images that actually make sense are unbelievably rare. And that brings us right back to the central mystery. If the universe of all possible images is this infinite ocean of noise, how do machine learning models so effectively find their way through it to find, understand, and even create that tiny, tiny fraction of points that actually look like something? And here it is. This is the answer: the manifold hypothesis. What it suggests is that real-world data, so pictures of dogs or human speech or stock market trends, it isn't just scattered around randomly. Instead, it all clumps together, forming these simple, elegant shapes called manifolds that are hidden inside all that high-dimensional chaos. To make that a bit more real, let's go back to that universe of TV static. The hypothesis basically says that all the possible photos of Albert Einstein don't just show up randomly everywhere. Nope. They all cluster together in one specific, highly structured little neighborhood. And the same thing goes for images of dogs or cats or any other real thing. So we keep using this word manifold. It sounds super complicated, but the core idea is actually something you deal with every single day. Let's break it down. Put simply, a manifold is just any space that, if you zoom in close enough, looks flat. It might be incredibly bent and curved on the grand scale of things, but right where you are, it's simple and flat. The absolute perfect example is the Earth. Right now, the ground beneath your feet probably looks pretty flat. You can walk in a straight line, no problem. But of course, we all know that on a global scale, the Earth is a giant curved sphere. The surface of our planet is a two-dimensional manifold. And this diagram just illustrates that perfectly. The gray curved surface, the one labeled M, that's the manifold. So think of that as the whole Earth. The yellow flat plane, that's the tangent space. That's the locally flat ground you're standing on. It's this simpler flat space that an AI can actually use to move around and make calculations. So why is this such a big deal? Because this one idea, this shift from trying to navigate an infinite, noisy space to just learning a smooth, simple shape, well, it changes everything for machine learning. Seriously, why is this so critical? Well, as this quote from Deep AI puts it, the manifold hypothesis is a huge reason why AI works at all. It tells us that the problem isn't about sorting through infinite noise. No, the data has a hidden structure, and if a model can just learn that structure, it can start to make sense of the world. So the AI's job is no longer this impossible task of understanding every point in a million-dimensional space. Instead, it's about finding and learning the shape of the dog manifold, or the face manifold, or the speech manifold. Suddenly, the problem becomes way simpler, more focused, and actually solvable. All right, so let's check out how this one concept unlocks some of the most impressive AI applications we see out there in the real world. Take 360-degree photos. The data from these cameras isn't flat, right? It naturally lives on the surface of a sphere. So an AI model that knows it's working on a spherical manifold, not a flat plane, can analyze and understand these images way more effectively.
And the exact same idea applies to 3D data. An AI can learn the underlying shape manifold of things like human bodies or animals. Once it gets that shape, it can generate new poses, reconstruct models from just a little bit of data, or even blend smoothly between different forms. It's pretty cool.
This is also incredibly useful for us, for humans. These manifold learning algorithms can take these monstrously complex high-dimensional datasets and squash them down onto a 2D surface that we can actually look at. This whole process reveals the hidden clusters in structures inside the data, and suddenly, we can understand it.
And really, the list just goes on and on. Finding similar photos in a huge gallery, generating brand new images, or recognizing what someone's doing in a video, all of these tasks are possible because the AI is taking advantage of that simple, hidden structure of the data manifold.
So if there's one key takeaway, it's this. The so-called magic of AI isn't really about having infinite computing power. It's about geometric insight. It's about the discovery that our incredibly complex world and the data that represents it has a fundamentally simple hidden shape.
And look, this isn't some fringe theory. As the research here notes, it is widely considered a key factor in the success of modern AI technologies. It's really the elegant assumption that makes so much of modern machine learning work.
Which kind of leaves us with one last big question. If something as messy and chaotic as raw data has a simple hidden shape, what other profound secrets are just hiding out there in plain sight, waiting for us to find them? Thanks for watching.